for those destinations you match here, you don't match here, what you can do is you do backtrack to here. But the worst case of the backtrack is you search all the line. So the length is still the number of bits in the address. So what this algorithm will do is actually for this, you pre-calculate in prediction that if you don't match anything here, I should be matching something here, I will just pre-calculate the result. So when actual search process starts, I will just do binary search. If there's a match go down, if there's no match go up, then after this do a search, I will be able to figure out what's the best match for me. So by doing this, what we can achieve is search originally, you need to like 700,000 entries to search to binaries, normal binary search like 32-bit for IPv4, 128 comparison for IPv6. Then what we can achieve is you actually can, for IPv4 you can do 5 comparison, you will find a match. For IPv6, 7 comparison, you will be able to find a match. Okay, that's the algorithm.
Great, thank you. Is that also used in IP tables, in firewalls?
Not really. It can be.
There's a sort of list of rules.
Yes, it's more like a destination list where you need to compare perfects. That's the kind of necessary.
Yeah. Yeah, it seems to me that there must be some fast algorithm for IP tables.
Yeah.
Because you can have hundreds, you can have thousands of rules.
Yeah.
And you have to test very quickly on every incoming packet whether it's a rule or not. So I've wondered about that. Well, thank you. I think I saw that once before, years ago, and I didn't remember it. So, again, brings things up to date. Now, Daniel, what are you going to tell us about?
The Fisher shuffle.
All right, good. Shuffle.
So, in my mind, that's kind of the inverse of sorting. Not quite, but that's what I think of. So, I was going to have a slide, but then my laptop died, as those things go. But I was given the great idea to use volunteers. So if I could get like at least 3 at some point when I ask, that would be awesome. Yeah, I'll ask in a second. So the Fisher-Yates shuffle is a super, super simple shuffling algorithm. And so what it does is it generates an unbiased permutation of a finite sequence, which is just like fancy way of saying to shuffle a deck of cards or shuffle, any list sequence type data type. And so what you do is you just iterate over the list with like a for loop, starting at the top index, and you work your way down. And at every index, you generate a random number between 0 and that index, and then you do a swap between those 2 numbers. And then you just work your way down to the first element. You don't have to do the 0th element because then it will just swap with itself. And then you're done. So you kind of split into 2 lists where your top of the list things that you've swapped in are your already shuffled part of the list. And so if I could get like 3 people, 1, 2, 3, awesome. So if you get in a line. So I've seen like in class we always do the like sorting of people, shuffles of people. So you're just 0, 1, and 2. I'll be 4. It's better with 1. And so we start with a pointer at me, and we pick a random number. So we'll say like 3. So
in what range between 0 and 4?
Between 0, if you have n elements, it's between 0 and n minus 1. Okay. Or well, you go from 0 to I, and your I starts at n minus 1 and you decrement each I.
Okay.
So we would swap. So we swap, and you're where you're at. And then we generate a number between 0 and 2. Okay, so it would have been 0 to 3. But we generate a number between 0 and 2. So if we say that's 2, then I stay where I'm at. And then now I is 1. And then say the number is 0, then you guys swap. And then you can only swap with yourself, so we stop. And now we have a random shuffle.
And is that guaranteed to give you probabilistically?
Yeah.
Same probability for any result?
Yeah, so if there are n permutations, then you have a 1 over chance of getting any permutation. So like if you ever use like the random dot shuffle method in the Python library, that's what it does on So I really like it because it's like, I think it's elegant in that it's O of n time, it's really fast, and it takes constant space, so it's really efficient. And it also kind of sounds like a really short-lived dance craze, like Fisher Yates shuffle. But yeah, that's it.
Thank you. All right, John, you got the Gale Shapley algorithm? Shapley. Sure, yeah.
Well, seeing that as it's Valentine's Day, I couldn't resist but talk about the Gale Shapley algorithm. When what it does is it is a matching algorithm between two equal-sized sets, and it's trying to solve a problem that in math and in computation is just called the stable marriage problem. So just envision two sets of, say, five men and 5 women. It could be any size n as long as they're equal. And for each one of these 5 men, they have a strict preference ordering of each of the 5 women. So it could be 2, 3, 5, 4, 1, or something, and for each of them. And same thing for the women. So there's 2 lists like that. And there are variants where you have only some of the lists preferred, or you have indifference between them, which turn out to be quite hard, so we're not going to worry about that. We're just going to deal with the simplest case. And so the algorithm works as follows. There is a group called the proposer, and there's a group called the proposed. Typically, you can do men being the proposer, but I'm going to mix it up and make the women the proposer. Doesn't really matter. So the first woman, woman 1, is going to look at her first choice, say man 3, and propose to this man 3. And I should mention that everyone is initialized to free at the beginning. The man 3 is going to take a look, and if he is free, then he has no choice. He must accept this engagement, as it were. And it goes on for each woman. Now say that woman 2 also has a first preference for man 3. Then what would happen is man 3 takes a look at his preference list, and between the 2, whichever he prefers more, he picks. So only one of 2 things is possible. Either he prefers woman 1 more, so at which point woman 2 is back to being free, and we go on. Or man 3 actually prefers woman 2 more, at which point woman 1 goes back to being free, and woman 2 is now considered engaged. And this keeps on iterating over the list until a stable pair of matchings occurs for all the women and all the men. And there are 5 nice properties of it. Number 1, it's always guaranteed to terminate. Number 2, it is always Pareto optimal. Number 3, it is always proposer maximal. That is to say, whoever does the proposing will always get the maximum amount of utility. It is similarly always proposed pessimal. They will always get the least amount of utility, unfortunately.
But it will be stable.
It will be stable.
So define stable for us.
That is to say, there is going to be, once this set of pairs comes out, there will be no man or woman who is going to be willing to renege on that engagement and find anyone else better for them. So there's no defection possible, essentially, is what is going on. And if you're very lucky, if everyone gets their first choice, it runs in O of n time, but in the worst case, it runs in O of n squared time. And that's the Gale Shapley algorithm.
I have seen a generalization of it for group marriages. You've got the men, the women, and I don't know, the chickens. And everyone wants a pet, right? So every family is going to get a pet, some chicken. But the chickens also have preferences, right? And so you can't generalize that. I don't know if the algorithm generalizes. The question does. And I wrote a program using answer set programming to try to solve the more general stable problem. As far as I know, it's completely useless, but it does exist if you want to ever try my program. Great. And Mr. Sagar will tell us about something or other.
So, I'm about convex-hull algorithm, especially Chan's algorithm, which is like not that old with respect to the algorithms that we are talking. Basically, I'm grabbing this opportunity to face my stage fear, so if this doesn't go well, never mind. Chan's algorithm is one of the very famous algorithms in computational geometry. It's n-log h algorithm. That is not the first n-log h algorithm. There was Kirkpatrick and Siedel's algorithm, which was also n-log h algorithm, but that was super complex. And what Chan did was just combined already existing like 30 years old algorithms and combined those algorithms in an intelligent way. So assume like there are 100 points, we'll just restrict ourselves to 2D. Assuming there are 100 points, we choose a constant m, let us say that is 5. We form n by n sets of points, so those will be like 20 sets. Then we form the convex-hull of these 20 sets, right? So entire algorithm is based on the assumption that my bigger convex-hull is combination of all the is a kind of superset of all these smaller subsets of convex-hulls. Then he uses any n-log n algorithm, especially uses Graham's algorithm to find the smaller convex-hulls. So complexity is n-log m. Then he uses another algorithm which is known as Jarvis-Marsh algorithm or gift-wrapping algorithm, where we kind of connect all the ends of the set of points, and kind of when we wrap the gift, it forms a convex-hull automatically. But he modifies the algorithm to use a binary search. So binary search is essentially log m algorithm. He makes certain assumptions that, okay, yeah, and another thing that while doing the gift wrap algorithm, he stops after m+1 steps. That is what makes this algorithm n-log h algorithm. H is the number of hull points in final hull, and n is the number of initial points. So why does he do that? Because if m is not, m is assumed to be smaller than the total number of hull points. If he doesn't stop at m+1, he might go on and on in order to gift wrap and might end up using all the points, which essentially kills the algorithm. The second trick he uses is choosing the m. M shouldn't be more than h, so m is like strictly less than h, but the increments of m has to be managed. If m increments are way too large, the Graham scan algorithm will take a lot of time and algorithm will blow up. If m is too small, it will take so many iterations to reach the solution that algorithm will blow up. So he uses something called as double exponents, which is like faster than exponents but slower than the factorial, and m is always updated based on 2 raised to t, t being the number of the current iteration, and that finally gives n-log h algorithm. Yeah, that's it.
Thank you. At this point, is there anyone else who wanted to tell us the algorithm? All right, let me set you a problem, and you have to come up with the algorithm. But we won't finish that today. I just want to tell you the problem. The problem is I'm thinking of a positive integer, and your job is to come up with an algorithm that will efficiently guess my integer. And your algorithm can only make probes, like you can probe 10, and I'll say, nope, that's too low. And then you'll say, 25, and I'll say, that's too high. And so I'll either say too low or too high, and eventually you'll get the number, right? But I'm not telling you how big my number might be, right? And so the question is, what is an efficient algorithm and what is its cost for that particular unbounded guessing of an integer? Okay? That's a problem for you. But now, let's take a vote. I'll remind you what all the algorithms were, and you'll get to vote for your favorite, but you can vote for however many you want. You can vote for them all, you can vote for none of them. We'll just add up how many votes. So certainly vote for your own. Okay? So to remind you, there was the KD trees for multidimensional data. There was the way of building the Bezier curves with 2 ends and a control point, or more than one. There's Meyer's diff, which is the way of doing a diff among 2 files and two strings. There's Bogosort, everyone's unfavorite way of sorting numbers. There's the IPA forwarding problem and how to go about avoiding doing millions of searches just as when you could do 7 instead. There's mergesort, using an iterative as opposed to a recursive method. And there's the amortized analysis of moving something to the front of a list every time you access it. There is the shuffle method. If you want to shuffle, get a perfect, not a perfect shuffle, but a perfectly random shuffle. Who's that due to?
Fisher Yates.
Right, this one in Fisher. There's the Gale, whatever it is, algorithm for stable marriages. And then there's this Chang's algorithm for finding convex hulls, right? Chan. All right, so now that you've heard them all, you get to vote. So how many people, now this is, you can have multiple favorites. Should I even list mine because I'm standing here? Yeah, I will. Okay, KD trees, I'll vote for that one. Okay, I see 12 votes for that. Jacob's one for Bezier curves. That's great. Okay, 13. Aidan's diff algorithm. That's a neat algorithm. Okay, hold your hands up while I count here. Okay, 7. I'm counting by 3s. I find that that's a very effective way of counting large numbers. Because it's easy by eye to see 3 at a time, then I just see how many times I saw 3. I recommend it. It's an algorithm. Okay, Bogosort. Okay, 5. IP forwarding tables. Too complicated for me. Okay, I'm seeing 5. Now, Dr. Truszczyński had 2. So firstly, iterative mergesort. 4. And always putting things at the front if you just looked at them. It's kind of nice. Yeah, it's easy to understand. I'll vote for that one too. 1, 2. Okay, 9. The way of getting a random shuffle. I wish I'd remembered that because I've always done it the wrong way. I'm going to vote for that, and I'm going to use it next time myself because I need it. All right, 7. Stable marriage, the Gale Shapley, or Shapley, whatever it is. Okay, 8. And the algorithm for the convex hull, the geometric algorithm, which I guess you can work at any number of dimensions, although you mentioned it in 2. Okay, I see 5. Great. Well, the winner is clearly Bezier curves. Well done. And come visit us again. I should applaud you for the awesome. Well done. I like the demo. Come back next week and stay current. Happy Valentine's Day, everyone. Have another cup.